Students, now today we are going to study speed of sound and derive Newton's formula, and we'll see what was the fault in Newton's formula, why was it not accepted, and what was the correction given by Laplace. So far you have studied about speed of a transverse wave in different mediums and speed of longitudinal wave in different medium. Now let us find out speed of sound. What was Newton's formula for speed of sound and what was its correction given by Laplace. So according to Newton assumed that speed of sound in a gas, or we can say sound waves, when they travel in a gas, they travel under isothermal conditions. Now, what do you mean by isothermal? You have already studied in thermodynamic. Isothermal means when temperature remains constant throughout. Okay, so there is no change in temperature. Now, how is this achieved here? He assumed that very small amount of heat is produced while compression. You all know that sound waves are longitudinal waves and they occur in form of compression and rarefactions. Now, when there are compressions, then some amount of heat is produced which is rapidly conducted to the surroundings, where during rarefactions slight cooling is produced. So initially if the temperature was T, which was high, then during compression, then after some time it is conducted to the surrounding where rarefactions occur and slight cooling is produced, which reduces the temperature and thus maintains the temperature. Both the temperature remains same and hence the temperature remains constant throughout. Okay, so using this concept, now we will try to find out the speed of sound in a gas under isothermal conditions. Okay, now first let us assume that we have seen so far that in longitudinal waves, when we talk about longitudinal waves, we have seen that what element of elasticity do we consider? We consider bulk modulus, or we use its coefficient of bulk modulus, which is kappa. So here coefficient of bulk modulus, which represents its isothermal volume elasticity, is K isothermal. Then according to speed of a longitudinal wave, we will get speed equals to under root kappa isothermal by rho, which is the density. Okay, you have already found this in case of speed of longitudinal wave. The speed came out to be kappa under root kappa by rho. So that is the same thing we are using, only we have replaced kappa by kappa isothermal. Okay, now if you remember, for isothermal change, the product of pressure and volume, it remains constant. Okay, now if we differentiating, let us say that this is equation number 1. Now differentiating 1 on both the sides, we will get and we are not differentiating it with respect to any other variable. We are just differentiating this expression. So first we will differentiate V, and after that we will differentiate P. So applying the chain rule here, P will remain constant, differentiate V, it will give you dV, plus now keep V as constant and differentiate P, it will give you dP. But this here it is a constant, differentiation of a constant gives you 0. So this is the expression you will get. Now using this expression, find out P. What will be P? P will be equal to minus V dP by dV. Okay, now can I write it like this? Minus of dP and take all the volume elements to once in the denominator. So this will give you dV by V. Is it correct? I hope you have understood this. Fine. Now if you look at this, What is dp? dp is the small change in stress. What is the stress? Force upon area. Okay, so this represents a small change in stress. And here, as we are talking about bulk modulus, so this will be volumetric stress. And you all know what is a strain? Change in volume upon original volume. So dV represents change in volume upon V, which is the original volume. So this gives you volumetric strain. Okay, so from here you have derived that P is equal to volume stress upon volume strain. But this is equal to bulk modulus of elasticity, which is K kappa isothermal. Okay, now this gives you the Newton's formula for speed of sound in gas. Okay, and as you can see, this expression, V was equal to under root of kappa isothermal by rho. Now replace this kappa isothermal by P, as we have derived P equals to kappa isothermal. So this will give us the speed of sound in gas equal to, in place of kappa isothermal, we'll write P upon rho. So this was the expression or the formula given by Newton for speed of sound in a gas. Now at STP, what is STP? At a standard temperature and pressure. Now what is standard pressure? We all know one atomic pressure is known as one standard pressure, which is also equals to 0.76 meter of mercury. Fine. Now if you put the value, you all know P is equals to H rho G. Now using this expression, this is the height 0.76. What is the density of mercury? 13.6 into 10 raised to the power 3. And what is the value of G? It is equals to 9.8. Now on solving this, you will get pressure equals to 1.013 into 10 raised to the power 5 Newton per meter square, which is equals to 1 atomic pressure. And what is the density of air at a standard temperature and pressure? It is equals to 1.293 kg per meter cube. Now putting these two values in this expression for speed of sound in gas, you will get V speed of sound equals to V is equals to under root of, put the value of pressure, it was equals to 1.013 into 10 raised to the power 5 upon density 1.293. Now when you will solve it, you will get this value equal to 280 meter per second, approximately equal to 280 meter per second. Now as you can see, we all have somewhere studied that at standard temperature and pressure, the speed of sound in air is equal to 330 meter per second, 331 meter per second. If we compare these two values, 280 and 331 meter per second, then 280 meter per second, which we derived using Newton's formula for speed of sound in air, is approximately 15% less than the actual value of speed of sound in air, which is 331 meter per second. That is why Newton's formula was not acceptable and there was a requirement for correction. Okay, I hope you all have understood. Now in next part we will study Laplace's correction of this Newton's formula, okay, which is equal to under root P by rho.